In this tutorial, I am going to discuss a very important topic of artificial intelligence, that is the game playing. Well, game playing is an area of research in AI from its inception, or I can say from the development of modern computer in around 1950s itself. The development of game playing has gained lots of attraction to the people of computer science. So let us see the overview of game playing. Game playing, besides the topic of attraction to the people, has close relation to intelligence and its well-defined states and rules. So here, when I mention the term intelligence and well-defined rules and states, it means that there are lots of games available in and around where for playing the games we require some intelligence. Suppose if I consider the game says for playing says, definitely before giving some moves by one player, you will have to think about from the perspective of the opponents. So if you will give one move, so what is the chance that that move will not be erased by the opponent? So for playing the says, we can define different states, or for giving the moves we can frame different sort of rules. Okay, so that's why the biggest areas of research in modern artificial intelligence is in making a computer programs or a player which can play on different popular games. But here I like to highlight is that we are not going to discuss about those sort of modern games like say PUBG or say GTA or say some shooting games where different computer graphics will be needed. Well, definitely we can apply AI techniques over there also for finding out some sort of path or for making some sort of decisions. But here in this discussion we are not going to discuss about that sort of game. So we can represent some of the games in terms of a game tree. A game tree is a layered tree in which at each alternating level one or the other player makes the choices. So we will see some examples of game tree. So that time the concept of game tree will be clear to you and why we need this game tree for some sort of popular games. So for the time being, it will be very important to know the structure of the game tree. So in its layer or in its level in a game are called the max layers, and another layer is available, that is the mean layer. So mean and max here, so max will be the computer programs or the computer, that means when the computer will give some moves, so that will be known as the max layer, and another is the mean layer. Mean layer is the opponent of the computer, that is the human being. So our main goal or our main motive is to design some programs for playing the games with a human, and we'll have to incorporate some human-like intelligence into the computer programs. So that's why we'll have to study the gameplay topic here. Well, let us come to the fourth point of game tree. So whenever we'll have to play a game start at the root with max play, and in the leaf node the game will end. The leaves of the game tree are level with the outcome of the game, and game ends over there. So let us see one example of game tree. So this is a game tree of 2-player, and as I mentioned that max is the computer programs and min is the opponent. So this is an example of tic-tac-toe game where the computer is trying to play the game with a human being. So in the root we are having the initial state, that means the 3 by 3 matrix, it is empty, right? So when the computer is trying to give the moves, so computers can generate all the possible moves from the initial state. So that means from this initial state we can generate, or the possible 9 moves are here. That means max can give the cross mark here, max can give here, max can give here. So in that order the 9 possible moves are available here. So suppose if max is going to choose this move, then definitely in the next phase min will give some other moves, right? So min can give, say suppose here, min can give here, min can give here. So in that order min has now 8 possible moves. So these things will go deeper, right? So if we can create the overall structure, so that is going to generate a tree-like structure, and that is the game tree. Now how many layers may be here? Because it is a 3 by 3, so definitely we can go up to, say, so in the factorial 9 possible, factorial 8, factorial 7, so in that order it will goes on, right? So in the terminal nodes we can have maximum number of factorial 9 number of moves can be, or the outcomes may be available there. So that will be a very huge number, right? And in the leaf node, if you observe here, leaf node, or it is known as the terminal, so here some utility values are given. So this utility value is signifies that if I consider this tiles position, so in this case the min has win the game, right? So that means the chance of winning the game for max is -1. Okay, that means max has lose the game. So for signifying losing the game for max, we can give one value like -1 here. Now in this case the game has draw, so that's why some utility values can be put here, that is 0. So 0 signifies here the draw, and similarly here +1, that means there is a chance that max can win the game, because max can put here, so there is a chance of winning, or the this tiles position is in favor of max. So this game tree has the size is exponential, but in our modern computer definitely we can generate this game tree, but the size is very huge here. Now if we think of one game like chess, so that time the, or if you want to design the game tree for chess, so that time the size will be very high. Okay, so in case of chess, so it is quite difficult to generate the whole structure, or for framing all the possible moves for the players is quite difficult, because in the first level for playing the games like chess, it will be number of moves possible in the first level for chess is 20, right? Then 8 pawn moves with 1 steps, then another 8 moves with 2 steps, then 4 knight moves for 2 nights, right? So overall total 20 moves are possible in the first level itself. Then the second level also it will be higher. So on an average, for playing a game like this, 50 moves are possible for the players. And here I would like to highlight one term called the branching factor. So in the initial phase, the branching factor here it is 9. Okay, that means possible number of moves. So from here also different branching factor, from here also different branching factor. So in that order, the branching factor also for the game like this is on an average it is 35. So the possible moves is 50 and branching factor is 35. So the moves are considered as the depth, and branching factor are another feature for calculating the complexity for designing the game trees. So let us see another example of game tree, like here also. So this box is representing, that means for the max move, and this is for the min move. So in that order we can generate a game tree like structure, and in the leaf node you can observe like it is L is representing the whether max is going to lose the game or it is draw, or W here it is representing the win. So that can be the representation. So if the game tree size is very large, so it is the computational cost become very high, because in again I'm repeating this thing. So which move max is going to pick up from this 9 choices? So can we apply some heuristics over there, or some searching techniques can we apply here, so that the computational cost will reduce? Okay, so which move the max is going to pick up? So for that thing, one technique which we can apply here for designing a human-like intelligence in the computer program, that is the searching techniques can be applied there, so that the best move will be picked up, and in lesser amount of time the computers can win the game or with some different outcomes. So the most commonly used AI technique is the searching, and the basic searching techniques for playing game like say tic-tac-toe, or like other games like say Sage also we can apply, but it will be very costly in that algorithm. But on an average, some 2 players game, if we want to incorporate one fundamental algorithms, that is known as the MiniMax algorithm. Okay, so MiniMax is a very important algorithm for playing 2 players game. So let us see the overview of MiniMax algorithm. So the most used game tree search algorithm is the MiniMax, and the MiniMax searches the game tree till depth k in a depth first search manner from left to right. That means we'll have to put a depth, that means up to which level the algorithm will search, and the searching mechanism the MiniMax algorithm usually used is the depth first search, and the searching is done from the left to right, because these are the features which are related with DFS. Okay, so let me go back to the previous example. So what is this depth here? Suppose in this case, for the time being, let us assume that Max has picked up this node, okay, or this position. That means in this position Max has give the move. Okay, so how Max has give this move? So for before giving this move, Max can up to say depth number, say if I'll consider it from this position, so depth if I'll pick up say 2, say it is 1, then it will be 2. So in this 1 and 2, the Max is going to calculate some evaluation or some heuristics will be applied by the program, so before giving any moves. So this sort of depth or some bound we can incorporate in the algorithm. That means up to which depth the program can think before giving any some sort of moves. Like in playing Sage also, that means before giving some moves, definitely one player always think. That means if I'll give the move here, then what is the chance that the opponent will not defeat me, right? So before giving any moves, the player always think of at least 1 or 2 level, or maybe say the third level. He thinks if I'll give here, then what is the possibility, then if I'll, so if then some clause he can put. So that is the depth. Okay, so that sort of depth we can incorporate in the MiniMax also. So the theory or the rule behind MiniMax is that the algorithm's opponent will be trying to minimize whatever value the algorithm is trying to maximize. So what is the meaning of these rules? That means the max always tries to maximize his value, right? Because he wants to win. And similarly, from the opponent point of view, max will think that so min, suppose if I am having the opponent, so min will not allow me to win, right? So whatever the value I am gaining, so that value min always try to minimize. And from the max point of view, max will always try to maximize the value so that max will win. So that is the strategy which is applied in MiniMax with depth k. Okay, so the functions which can be used in MiniMax algorithms. So MiniMax can be designed using the recursive procedure. So recursion is a function which calls itself. So in MiniMax we can have two important functions we can design there. One is the moveGen and another is the static evaluation function, or that is known as the heuristic function. So the moves, the role of the moveGen function, that means, again I am going back to the previous slide. Suppose in this case, in the initial state, if I want to apply the moveGen, so moveGen will generate all the possible moves. Okay, all the possible moves. That means 9 possible moves are available here. So that is the role of the moveGen. And in this position, suppose in this position, how many possible moves are available for one particular player. And before choosing any, that means whether in the initial state max will choose this or this. So for picking up the moves, one evaluation function will be used or one heuristics function will be used, and it will be done recursively. So these are the two functions, moveGen and static function, which can be inside the MiniMax recursive function. So let us see the pseudocode for MiniMax function. So we can have a function called MiniMax. So we can pass 3 parameters here. One is the present position or the state, then what is the depth that we want, and who is the player, whether it is max or whether it is min. So initially it is for max, so max is true initially. Okay, so if depth is 0 or we are in the ground level, or that means in the leaf, so that's why depth is 0 over in some position, so definitely we'll have to return the static evaluation of that position. If the turns is for max player, so what we'll have to do, we are taking one variable here, say maxval. So initially the value of maxval is minus infinity. That means in the worst case scenario the value of maxval is minus infinity. Then as it is the turn for max player in some particular position, so we'll have to generate all the possible moves. So for each child of that particular position, we are again calling the minimax. Okay, that means we are passing the child, then definitely depth will be -1, then we are going to the next level, that is the false, and we are calculating the evaluation. That means we are taking some values, then we'll have to find out the max of this max eval and this whatever the this minimax has returned. So whatever the max value will be there, that will be passed into the max, and that value will have to return for a max player. So with one example in the next slide I will discuss properly. So if the turn is for mean, so else if it is a mean, then we'll take another variable for mean is say the value is positive infinity in worst case scenario. Okay, because in worst case the mean value may be very high, and in worst case scenario max value may be very low. So again the same things for the max, it will be repeated. Like for mean also we'll have to generate the children for that particular, then we'll have to call the minimax, then we'll have to find out the mean, then we'll have to return the mean value. So that is the pseudocode for minimax function. So here we will have to use the static function. Here we can generate the moves and function. So let us see one example here. Say this is a particular position. So in this position we will like to calculate the values. Okay, that means in which direction max will move. Okay, so in this particular position it has two children like this one and this. So again this move has, again it will call in this max, it has generated the children. Now it is the mean turn, mean again is going to evaluate, then again max, so max is going to evaluate, then again mean. So mean has suppose generated and it has reached the depth here, suppose it is 0, so it is the leaf. So here the evaluation values are say for this particular, because it is a DFS, so it will go come like this in the left hand side, so it will come here. So after that there is no children, so the evaluation function is called there. So it is 0 and 7, suppose it has two possible moves, right? So here the mean value is, so let me see the code here. So mean value here in this case it is positive infinity, right? So mean has evaluated this, again it has generated min max. So mean eval is infinity, positive infinity, and the value here eval here it is, for this case it is 0, right? So 0 and positive infinity, so which one is lesser? So definitely 0 is less, so in this case 0, right? Again it will come here, so it will compute here, so minimax will return 7, right? Now it will be compared with 0 and 7, so which one is minimum? So 0, so in this case the value here will be 0. So mean will return from this two evaluation function, that means two children, it is 0, right? Now this value will be come to max, right? Now for this max has generated this, so which value max will pick up? So minus infinity and 0 will be compared, so definitely 0 is higher than minus infinity, so max value, that means for this here the value will be 0. So again it will go down, again it will be called, so 9 1, the value is 1, right? So for 0 and 1, which one is higher? So 1, so 1 will come, then again it will here 6 and 0, 6 and 7, 6, so 1 and 6, so 6, so 6 will be here. So in that order the overall minimax will explore all the possible things, and for this 6 and 3 the max minimum value is 3, then again it will come here, then again it will come this side, so it will go deeper. For 9 and 2 mean value is 2, it will come here, so in this direction 2 and 3, for 2 and 2 the max value is 2, so it will come here, it will come this 4 and 1, so 4 and 5 it is 4, 4 1 and 2 it is 1. So this procedure will be continued until the value will be backed up to the for this particular position. So finally max value will be 3. So max may go this direction, so that if max is going to pick up this side, so there is a possibility of winning that particular game, or in this tree that can be considered. Okay, so let us see another example of MiniMax in tic-tac-toe game. So in tic-tac-toe, it is a 3 by 3 matrix presently we are considering, and for max we'll have to put the cross mark, for min we'll have to put the 0 mark. Okay, so here one static evaluation function is used for some particular board position. So the job of this static evaluation function is that number of direction open for max minus number of direction open for min. Okay, so if max is going to win, we are putting for the evaluation function as say inf, and minus inf if min is going to win. So these are some say static value we have just put it here. So to understand the heuristic function, let us take one example how it works. Say in this position, if you want to calculate the heuristics value or the static evaluation function, so how many positions are open for max? So x has 6 possible input, that means x can give here, x can be here 2, x can be here also, x can be here also, x can be here, x can be here. So 6 possible moves are possible for max or for x, and 5 possible wins or moves are possible for this, for putting zeros here. So the evaluation function will be 6 minus 5, it will be 1. So similarly we can have other 2 examples are shown here for understanding the evaluation function. So let us consider that this is the position which we have reached after giving some moves in the tic-tac-toe game. So in this position, if we want to calculate the evaluation value, in which direction max will move, so presently from this position max can go this direction, so 5 possible moves are available for max. So max can give here, max can give here, max can give here, max can give here, max can give here. Okay, so which move max is going to choose? So for choosing any sort of position, the base move, what max is going to do is that max is going to go little bit deeper. Okay, and it is trying to compute the evaluation, and it will be backed up to the max, and in that order max will choose the particular move. So let us compute the possible moves for min here, because max is going to evaluate, because it is going to compute some evaluation. So for getting the evaluation, it is going to generate the min moves also. So from this particular position 4 moves are possible for min, right? So in this case, what is in now in this position, if we want to calculate the evaluation value, so our evaluation values or evaluation function says that number of position open for max minus number of position open for min. So number of position open for max is one this direction, right, and another is this direction, because if max is going to give in this point, so there is a chance of winning, right? So 2 moves, and one possible moves is opening for min, this is the this direction, so that is 2 minus 1. Similarly for this tiles position, so one is this direction, one is another this, another is this direction. So 3 open moves are available for max for winning, so this is 3, and this is the 1, so that is 1, so it will be 2. Similarly for this tiles position, this is open and this is open, so 2, and this one is another open for min, that is 1. Similarly for this is the open and this is the thing for max, so the value will be 3 minus 1, it will be 2, right? So we have got 1, 2, 1 and 2, so these are the evaluation value, right? So what do you think, which value mean will going to pick up? So definitely from this 4 values, minimum value is 1, so mean will pick up 1, so this value will be 1, right? So similarly we'll have to compute for this other 4 position. For this position also in similar way we can compute the evaluation value for the mean moves. So if we compute this, so it will be minus inf, right? Because it is draw is for, that means not draw, mean is going to win, right? This minus inf is representing mean wins. So similarly it is 1, it is 0, it is 1, so mean definitely is going to pick up the minimum value or his win value, so it will become here. So next time we'll have to compute for this. So in the next slide, in this slide we are having the calculation here. So again the mean is going to return minus inf. In this position it is minus inf, and in the last position also is minus inf. So this is 1 and rest of the values are minus inf, right? So which move max is going to choose? This is 1, this is minus inf, minus inf, minus inf, minus inf. So the among these 5 values the maximum value is 1, right? So max definitely is going to pick up this one, so max is going to follow this path rather than following this, because max has come to know that if he is going to pick up any of these 4 available path, he is going to lose the game. That means the program is going to lose the game, so program will pick up this path by using this MiniMax algorithm. So in the next phase we can have different moves will comes, and in that order max will follow. Okay, so this is about MiniMax. Now let us see the computational cost of MiniMax also. So if the maximum depth of the tree is d and there are b legal moves at each point, then the time complexity will be order of b to the power d. Okay, and it is exponentially, it is going to see all the possible moves, so that's why the computational cost for MiniMax is b to the power d. And similarly we can compute the space complexity, it is order of b into d, so bd is the space complexity. So is there any possibility so that we can reduce the computational cost? So the problem with MiniMax search is that the number of game state it has to examine is exponential in the number of moves. So we can have an improved version, or we can give some enhancement in MiniMax by applying the concept of pruning, or by applying the concept of cutoff, and that is known as the alpha beta cutoff. So let us see the improved version of MiniMax. So alpha beta cutoff or pruning is one technique which is used in MiniMax so that unnecessarily some of the branches of the tree will not be explored. Okay, so it is possible to compute the correct MiniMax decision without looking at every node in the tree, and the idea of cutoff is applied here. So the basic idea is that if you have an idea that is surely bad, don't take the time to see how truly awful it is, and it was mentioned by Pat Winston. So the alpha beta cutoff, the idea is that when the max player comes to know that mean player is not going to give good moves, so max can cut the branches of the tree. And similarly, when mean is comes to know that max player is going to give some good move, so mean can cut the branch of the tree. So that is the idea. That means max will cut his moves when he comes to know that after this move the mean is not going to give, or there will be no probable good outcomes, so it will cut down the tree. So applying alpha beta cutoff, we can reduce the computational cost by not exploring some of the branches of the tree, right? So let us see the technical things about alpha beta cutoff. So alpha value is related with max and beta value is related with mean, and we'll put some bounds. That means alpha is actually a bound kind of things and beta is also a bound kind of things for mean. So alpha values at max node never decrease. That means if max has got some alpha value, so after getting the value, the max value will not decrease, but the value can increase. But after getting in a particular position, if max has got some value, so from that value the max value will not be decreased. So that's why it is known as the maximum lower bound for some possible outcome. For example, suppose if the value of alpha is 3, then below 3 it will never go, but it can increase, okay? And beta value at mean node never increase. That is minimum upper bound for some possible outcome. So similarly, if the beta value is 3 for a particular node of mean, then above 3 it will never go, okay, but it can decrease. So to understanding the alpha beta, let us take some example, then I think it will be clear. And another condition we will have to check in alpha beta cutoff. So let us see the condition. So to keep track of alpha and beta values, we can state the following rules. So how we can eliminate the search? So for that thing we are having one rule. So searching will be eliminated below any mean node with if the alpha value is greater than or equal to beta. So one of its max node ancestor. So we can set the final value of the node to be that particular beta value. Similarly, searching will be eliminated below any max node if the alpha value is greater than beta of one of its mean ancestors. So these rules can be framed. So alpha value is related with max, beta value is related with mean, and we are having one condition is that alpha is greater than or equal to beta, so that time we'll have to cut down the branches of the tree, okay? So for understanding this alpha beta cutoff, so let us go through one example. So let us consider that in a particular position for max we want to apply the alpha beta cutoff here. So in this position max has one possible move, right? And initially alpha value is assigned with minus infinity, that is the worst case value, and beta value is assigned as positive infinity, like in MiniMax, because in MiniMax only we are going to apply the alpha beta cutoff, right? So this alpha and beta value will be passed down to the kids or to the children. So in this case mean is going to, because this upper triangle is for max for the time being and this lower triangle is for mean, okay? So alpha beta value is passed, now mean turns to mean has this. So in this case suppose we want to evaluate the value. So what is the evaluation value? Let us see. So whenever it will get some values, so it will be compared with the values over here. So it is 3, right? So 3 will be updated for the beta value. Okay, because 3 is, again I'm going back, beta value presently it is positive infinity, and value that we have got here it is 3, right? So which one is minimum, 3 or this positive infinity value? Definitely the minimum value is 3, right? So beta value will be updated here because it is for mean term. So this value 3, so mean value here it is 3 now. Now it is going to check the mean is, for this again we are having two other possible moves are here, right? So it is 12, so 3 12, so again minimum value is 3, then again we are having 8, so minimum value here it is 3, so mean is going to pick up 3. Now this 3 will be backed up to the max. Now max value is going to become, that means the alpha value will be updated now, then it will be 3. Again I'm going back, so here alpha was minus infinity, right? And beta value finally we have got as 3. So this 3 definitely max which value the max is going to pick up. Max is going to be picked up 3, right? So 3 will be backed up and alpha value is going to pick up 3, because it is going to, max is going to compare 3 with minus infinity, so 3 is higher than minus infinity, right? So max value will be picked up with, max is going to pick up alpha value as 3. So alpha value is 3. Now again there max is going to see for the other possible branches or the children of max. So there is another, so max has another possible children, this one. So again here mean is going to mean term, right? So mean, so alpha value is 3 and this evaluation value is 2. So 2, the beta value will be updated now, it will become 2, right? Now again mean is going to check for the other possible values here, right? Now in this case you can see here the alpha value is greater than beta, and what was our condition? I am going back here, so alpha value is greater than beta, right? So that condition is satisfying there. So whether shall we have to explore the branches here? No, we can cut down the branches here. So whatever the possible moves are here, so we are not going to explore these branches because the value of alpha here it is greater than beta. Okay, so cut off. So there may be possible that different branches will be here, right? So this possible, whatever the values are here, so all these branches are cut down. That means somehow the computational cost is reduced here. So which value will be backed up? So alpha value again will be backed up, so it will be 3, right? Because it has not changed. Okay. Now again, because alpha has come to know that the value will not be decreased, okay, because alpha value has 3, so max will never decrease below 3. So that is the bound, upper bound. In this case also for mean value will never decrease to lower than 2. So that was the bound for mean. Now it is going to other branches, and for this tree we are having another children. So alpha value will be passed to the children. Alpha is 3, beta is positive infinity now. Again it is going to check for the mean is, now it is mean turn, mean is going to mean move. So 14, so 3 is not greater than 14, so it is not it is going to expand the other branches, right? So beta value is 14 now. Now it is 5. Is 3 is greater than 5? No, so we cannot cut down, we will have to expand. And here earlier value for beta was 14, right? Now the value is 5, so 5 is smaller than 14, so that's why the value of beta is also changed. Okay, now another possible is 2, so 2 and 5, the minimum value is 2. So in this case for all the children of max 3, 2 and 2, so which value max is going to pick up? So 3 will be picked up. Okay, so the max value here will be 3, that means in this direction the searching will be goes on. And here we can observe that means 2 branches of the tree is cut down using the alpha beta pruning here. it okay? So 3. So max calculate the same node value and makes the same move. Now for the tic-tac-toe also we can apply alpha beta pruning, and definitely the branches of the tree will be reduced and the computational cost also is going to reduce. So in the initial, from the initial state point of view, if you see here in this example only 3 possible moves are shown, this one, this one and this one, but from the initial state we can have 9 possible moves, but due to limitation of the slide I am just showing only 3 moves. So if this is the max move, right? This max, this is max, this is max. So which move max is going to pick up? So it is going to expand. These are the mean. So if we calculate the values here, so minimum value here it is -1, right? So mean is going to back up -1 here. So from this thing mean is going to back up -2, -2, and from this move also minimum value may be -1. So 1, -2 and -1, right? So max, usually which move max is going to pick up? It is 1, right? Now can we apply alpha beta here also? Now if we apply alpha beta here, so mean is going to apply. So let us see in the next. So in the red block I have shown that this can be cut down, these branches, overall whole branches can be cut down. Okay, so in this case, so -1, right? So this value will be backed up as alpha value, this will be -1, right? So this value will come down, so beta value will become -1. That means in this case -1 will be beta value, right? So -1 and alpha value is -1, so -1 greater than equal to -1. So all these branches we need not have to expand. So that's why here it is not shown, and in the previous slide I have shown as like in a red marker, it is shown here. So in tic-tac-toe also it will be very beneficial if we apply alpha beta, then the number of branches for playing the game will be reduced. So this is the theory for this tic-tac-toe game. Just as a theory I am just showing it here, okay, just for the explanation purpose. So this is another example, like for initially alpha is -infinity, beta is +infinity, so it will be come down here. So with our previous concept, these things can be applied here, and finally these branches can be cut down, right? So this is another example. Well, so in this discussion I have mentioned about earlier the MiniMax, right? Let me go to the previous slides. So initially we have seen the MiniMax algorithm. Then MiniMax is a recursive procedure which uses internally 2 functions, moveGen and static evaluation function, and we have seen the example of MiniMax. Then we have seen the example of tic-tac-toe with a particular box position, right? Then after that we have seen some of the some observations related with MiniMax. It has some disadvantages, so to overcome this we can have the concept of alpha beta pruning. So the alpha beta pruning, alpha is related with max player, mean, and with mean beta is related, and we have the rule of alpha is greater than or equal to beta, right? So alpha value at max node never decrease, and beta value at max mean node never increase. So this is the concept which can be applied. So with 3 examples I have shown how alpha beta pruning can be applied. Now the effectiveness of alpha beta cutoff. So in practice the branching factor can be reduced, okay, up to d/2, rather than b to the power d, and d here it is the depth. For say game like Swiss, the branching factor is all in average, it is 35, and the move or number of depth here it is 50. So for game like Swiss, the value can be 35 to the power 50, which is a very huge number. Okay, so by using alpha beta pruning, some of the research papers has claimed that the branching factor can be reduced to 6 only. So it has lots of impact in computational cost in terms of space and time. So that is the effectiveness of alpha beta pruning. So these are the references which I have followed for designing the tutorial. So I hope with this tutorial you have come to know how MiniMax algorithm is applicable and how alpha beta pruning can be efficient over MiniMax algorithm. So thank you very much.